Now that we've kind of discussed what quality assessment is, we're going to take it a little step further and we're going to start talking about quality control within the clinical laboratory setting. Now, while your quality assessment policy is going to look at the three phases of testing, the pre-analytical, analytical, and post-analytical phase, your QC is looking at just that analytical phase, so your actual testing phase of that patient specimen. And so there are two types of QC, or quality control. We have internal QC, and then we have external QC. With your internal QC, this is going to be more of a statistical thing. So it's going to look at your daily process, your daily precision and accuracy of that test method, of what you're doing to measure that sample. Your external QC is going to look at the accuracy of that particular measurement or that test method. And so this type of QC uses that PT testing. It uses voluntary submissions of internal QC. So there's a couple of different things that we can do for that external QC process. Part of that would be taking your internal QC and submitting it to a peer review type group. Now, this isn't required. This part is kind of voluntary, but a lot of labs like to do this because they like to see where they sit with other organizations, with other people that are running the same QC material on the same analyzers. So it kind of gives you a little extra data to help with that quality assessment process. So this would be something that could be done in addition to that proficiency testing that we mentioned earlier. Documentation of all of your QC is going to include things like preventative maintenance, temperatures, any sort of QC charts, any sort of error documentation. All of that is going to be included in your QC policy, procedure, and documentation. So quality control itself is going to test your particular test methodology for that particular analyte. So when I say an analyte, I'm talking about a particular individual test. So an analyte could be something like a glucose, or a hemoglobin, or hematocrit, or a particular liver function test. So when we do QC, we do it on a particular analyte, and we look at that analyte as an individual versus an overall test panel. A quality control material is going to be something that's going to represent whatever you're testing. So with a urine quality control, the specimen that you're testing as your quality control material is going to mimic urine. If you're doing a chemistry test and you're doing something like a glucose, then that quality control material, that matrix, is going to resemble actual serum or plasma for that particular test method. So what it does is it comes from a manufacturer, or most often from a manufacturer. There are some scenarios where you may have to make up your own quality control material, but for the most part it's going to be from a separate manufacturer who is going to devise some sort of quality control material that they'll send you that you will use to assess your particular analyte on a daily basis. And so what it does, quality control does, is it's a way to detect errors that could happen within the instrument itself or the particular equipment that you're using. It's going to look at the reagents that you're using, so it's going to kind of help you evaluate if those reagents are still good, that there's not a particular error with that reagent or possibly in the preparation of that reagent. And it's going to look at individual techniques. So it could be a testing technique, it could be the particular staff member that is running the test for that day. It can help catch errors like staff that are doing tests improperly. So your quality control is going to kind of help evaluate several steps within that analytical process. It helps to confirm the stability and accuracy of a particular testing method when you compare it to the reference values. So making sure that that QC material falls within the limits that are established for that QC material when you run that particular QC material on your analyzer. Does it fall within the reference ranges for that particular QC material? It's going to help you detect any sort of increase in frequency of both high and minimally acceptable values. So it's going to assess that dispersion. Are you able to send out values that are on the low end or on the abnormal side of low and the abnormal side of high? Is your particular method going to detect the high end and the low end? It's also going to look for any sort of drift in values. So things that could affect your test method. So things that kind of happen over time, the deterioration of reagents, deterioration of controls, your light source in your analyzer, or other things that might be going on in your analyzer with parts malfunctioning inside your analyzer. Maybe your pipetter inside of your analyzer, the pistons on it are starting to wear down and things like that. So it's going to kind of help you start seeing trends and things that are happening. It kind of gives you a visual picture to see if it's something that could be affecting those results. You can kind of get a visual to see that something's happening over time. And we're going to look at some of these things as well. It will also demonstrate an abrupt shift in something. For example, maybe everything's been running normal, and all of a sudden today your QC values shift up. They're still normal, but all of a sudden you've got a shift in something. So you might have to do some investigations to figure out what has all of a sudden caused that shift in my QC values. So let's look at some of the descriptors that we're going to have when we're doing quality control and some of the things that we look at. So accuracy describes how close it is to the actual target or true value. So when you get a sample in for QC and you run that sample, you're looking to see how close you got to the actual value that was established by that manufacturer. So this is going to check your accuracy. How often do you hit that value when running it multiple times, back to back to back? Are you getting close to that center point value every time? And so if you're looking at accuracy, it could mean that if your accuracy is off, that maybe it's time to calibrate. So your calibration is going to kind of give you a set standard for that particular analyte. And so when we're looking at calibration, this is going to kind of be your constant. Anytime that you run anything on this machine for this value, this is what it should be. And so calibration standards are sent out and have to be performed on a machine to kind of set the center point value for that particular analyte. And then your control is going to be part of your daily thing that's going to assess whether or not you're hitting that point every time. And so it's going to be a known thing, a known control value. It's going to kind of represent a high, a low, and a normal. And it's going to represent that blood sample matrix or whatever test method you're using. If it's not a blood sample, it could be a urine sample. And so that quality control material, you're going to run it at specific intervals depending on what your plan is for your laboratory. It could be once a shift, it could be once a day, whatever's established. You're going to run that quality control material and run it just like you would a patient sample, and it's going to look to make sure that you've not had any variations of that analyzer. And if you do start seeing that the quality control is starting to shift a little bit, then you may need to start looking at some things and doing some adjustments. Part of that quality assessment plan is to look at precision. So precision is going to be how close those test results are to one another if you repeat it multiple times. How, even though they may not be accurate, they may not be close to the target, you're still repeating and getting the same value over and over and over and over again. So this refers to your reproducibility, the ability to run a result multiple times and get the same result. So there are some standards that can be ran that will actually assess this. And so it's a little bit different than the control that we use to do this reproducibility study, but this is something that is done within the laboratory to check your precision of your machine or precision of a particular test method. And so this not only is usually going to help you with precision, but it's also going to kind of help you a little bit with your accuracy, to see where you are. And if you start running your reproducibility studies and you kind of notice that, hey, yes, something's a little off, I'm not getting the same thing, then it's going to kind of help you to point out that maybe you need to look at something in your methodology to see if there's something that's going on with your analyzer or your methodology that you need to look into. So let's kind of talk about the difference between accuracy and precision. So with accuracy, you're looking at how close you are to the actual target value. So if you're given a particular target value for a test, let's say we're talking about a hemoglobin test. And our hemoglobin for our low QC level is 6.0. And so we run our test multiple times and we get maybe a 6.2, a 6.3, and maybe we get a 5.8. And so while they're not exactly on target, they're pretty close. So they're pretty accurate. But then with our precision, it's how many times we can run it, repeat it multiple times, and those values stay pretty close together. So maybe our value is 6.0, but we're getting a lot of 5.7, 5.8, and 5.9s. So they're still pretty precise. We're getting them pretty close together. They're just not on the target. And then if you're looking at something to be accurate and precise, then hey, we got 6.0, 6.0, 6.0. So we repeated it multiple times, got the same value, and not only are we getting precise results, they're also accurate because they hit the 6.0 target value that we were looking for. And so when we look at precision, this is going to help us determine our standard deviation and coefficient of variation. So with this, we're going to kind of go a little bit more in detail as we look at the whole QC and quality assessment program. The variance is a general term that just describes the factors or the fluctuations that can affect a measurement of a substance in question. So in this particular example, we notice that our precision is pretty good, but it's not accurate. Then it can kind of help us look at a few things when we're comparing results of QC material or patients. So we're going to look at all these things in a little bit more detail. So in understanding this whole process, we need to kind of talk about some of the terminology. So when we talk about true positive, this is basically a patient that is known to have a particular disease and they test positive. That particular test proves that, yes, it is a true positive, this patient truly has this disease. In the same aspect, a true negative is a patient does not have this particular disease, so we expect a negative result. However, on the other hand, a false positive would be a patient that tests positive even though they don't have the disease. In the same aspect, a false negative would be you get a negative result, but the patient really does have the disease. So an example of this, while it's not really considered a disease, would be a test, for example, an HCG urine pregnancy test. So with the HCG urine pregnancy test, you have areas where you can have false positives and false negatives. So example of a false positive would be the patient's not pregnant, but yet they're given a positive urine pregnancy test result. And so there are things that can cause this. For example, if a urine HCG pregnancy test was ran on a man and it came up positive, well, we don't expect that that man is truly pregnant. However, it could be a false positive due to a particular disease state that will cause a man to produce that hormone, and that is a particular type of cancer that causes that hormone to produce. So if you were to get a test on a male patient for a urine pregnancy test, you might question it. You might ask the physician, hey, did you truly want a urine pregnancy test on this patient? I've got it showing in the system that this is a male patient, and they may say yes. we're suspecting that he may have this particular cancer. The same aspect, I've had situations where that's happened, and when I call to ask about it, someone ordered the test in error. So again, that's part of that quality assessment, because it could have been possible that we could have ran that test and insurance wouldn't have paid for it. So that's going to fall back on the patient because someone clicked the wrong test when they were ordering something. And I've also had it before where that scenario has happened, and when I called and questioned it, someone had actually put the sex of a patient into the system incorrectly. With a false negative on a urine HCG, those urine HCG levels double about every 2.5 days. So it could be that the patient is pregnant, however, that level in the urine has not reached to a point where it is detectable in the urine sample. So most of your urine pregnancy tests will detect at about 20 to 25 for that urine HCG level. So if your patient is at 15 and they've not quite reached that threshold yet, then they may not, they're not going to show positive on that particular test method. So that's where it's recommended, maybe if you suspect that the patient is truly positive, then you might want to do a qualitative test. You might want to skip the qualitative test, which is that positive or negative value. And so when you think about qualitative, qualitative does have an L in it, so that's a letter, positive or negative. Whereas quantitative, if you were to do a quantitative test, you hear that N in there, and that means you're going to get a number. So doing that quantitative test for that HCG level would actually give you that 15 value versus that negative result. So you would actually get a numerical result. When we're talking about sensitivity and specificity, we're looking at things like with sensitivity, how sensitive it is that particular test method to detect what we're looking for. So again, going back to that urine HCG, if the positive result doesn't happen to the patients around 20 or 25, depending on the particular test manufacturer and what their detection limit is, yes, that test is sensitive to detect HCG, but only at a level of 20 or 25 and above. So anybody that comes in at a 15, it's not going to detect that lower level. So yes, it's sensitive to a certain percentage. So its sensitivity level may be at like 80% versus where your quantitative method, where you're actually getting that number value, is more sensitive. It's about more like 99% sensitive. Your specificity is going to tell you how specific is that test to detect that particular disease or analyte or positive results. You're looking basically with your specificity to be able to rule out something. So is urine HCG specific for the HCG hormone? Yes, it is, but you also know that you have some room for some false positives and false negatives. So you kind of got to keep that in your mind, that just because the result comes back positive, it is specific for that HCG hormone, but there are some other things that can give you false positive results. For example, tumors, molar pregnancies, things like that. So even though you get a positive result and you think, okay, this patient is pregnant, you still got to kind of keep in your mind that there are other things that cause that specificity of that to be a little bit less, because it can detect other things. Some of the other things that we look at when assessing a test method is predictive values. So if you run this particular test in your lab, what's the chances that it's actually going to predict or detect a disease in a patient population that actually has that disease? So this is something that's kind of assessed by the manufacturer of that particular test method, that they're looking at a particular population and seeing how often they actually get those data results to correlate with that patient disease state over a period of time. So a positive predictive value is the number of patients that would have that abnormal or positive test result or negative test result who have that disease. And so there are some statistical analysis that are done to see where they fall with that disease state and how they demonstrate that on that test result. So your predictive values equal the number of true positives divided by the sum of true positives plus your false positives. So this is what this manufacturer is going to do to kind of help promote the sale of this particular analyte. And then they're also going to give you the negative predictive values, which is going to be the number of patients with the normal test result who do not have the disease divided by the total number of patients with a normal negative result. So they're going to look at a lot of different factors, and then if you're looking to add a particular analyte or a new test method to your laboratory testing profile, then these are some of the things that are going to be looked at. Because if the predictive value is very low for this particular analyte, you may want to consider, hey, you know, it's not going to benefit us a lot if we can't trust these values, so you might decide to go with a different manufacturer. So now we're going to get into kind of the meat of what quality control is. And so by doing that, there's a lot of statistics that are involved. So when we do quality control, some of the analytical data that goes into it's going to look at things like your mean, median, and mode to help you assess your quality control plan. And also in that, we look at standard deviations and confidence intervals. So these are some of the things that you're going to do when you're doing your online lab for this unit, is doing some of these calculations and looking at what actually goes into your quality control. So by doing the mean, we're going to first determine what is the average of the group of numbers. And so with that, we'll add everything up, we'll get our average when we're doing some quality control assessments. And then we're going to determine the median. What is our middle value of all of those data points? And then we're going to look at the mode, which is which of those data points do we get most often? And once we kind of get these values, then from there we're going to start doing some calculations, and we're going to determine our standard deviation. And what this does is it measures the variability within our data set. So it kind of gives us a range of what we can feel comfortable with. If it hits between this point and this point, then we can say that, hey, this is pretty accurate, pretty precise, and we can send these results out. And then we're also going to look at what's a confidence interval. So when we talk about a particular reference range or a particular set of values that we want to kind of stay within, once we determine that standard deviation, then we would say, hey, I want to stay within 2 standard deviations, because that gives me about a 95% confidence level that what we're doing and sending out is accurate, that we're sending out quality results. So when we talk about that 95% confidence interval, then what we're looking at is about 95% of our data should fall within this range. So it's a statistical figure. And so what that does is it uses that normal bell-shaped curve to kind of assess our data. So it gives us, with the highest point in the center there, so you can kind of see that little, that mean there in the center. This would be considered your mean here, the center point, this high point. And then on either side of that mean, it starts to decrease. So you see that kind of, that Gaussian curve, that bell distribution where it kind of levels out on either side. And so we use this with a variety of measurements, even beyond outside the clinical laboratory setting, to kind of assess data. And so once we get all of our statistics, then what this kind of tells us when we're looking, depending on what we're looking at, but let's just say we're looking at a normal, healthy population, that most of the people should fall within this 90% interval, or this 95% interval, within 2 standard deviations. So once we do those calculations and determine what those standard deviations are, then we know that 95% of our normal population is going to fall within these 2 standard deviations plus or minus. So they're either going to be above the mean, that center point, +2, or they're going to be below the mean, below that center point, -2. And so this is where most of your population should fall. Now when you go beyond that, when you start getting to the +3 and the -3, then you know that most of your people, pretty much anybody that you would run, should fall within that category. However, that's not really considered normal. Once you start getting out beyond the +2 and the +3, these are going to be more of your abnormal values. So we use these statistics when we're looking at reference ranges for patient populations, as well as when we're trying to determine our ranges for our QC methods. So again, this is all statistical. One of the things that we look at is total analytical error. So we're looking at the overall process to determine how accurate and precise a particular test method is. And so this kind of establishes what we deem acceptable as far as the possibility of errors within our particular setting. So the FDA recommends that manufacturers evaluate the total analytical error when they're evaluating a test method. So when they're getting ready to try to market this and get it FDA approved, the FDA wants them to look at the combination of errors from any sort of source that could come in. So this could be random errors or systemic errors. So it could be, random errors caused by someone just making an error when they're running the test, or systematic errors in that actual test methodology, something in that process during that test that could go wrong. And so when they do this, they use a coefficient of variation, which again is a statistical figure. When they're looking at that particular percentage to determine, what particular errors could happen and what could be the consequences of it. So that statistic right here that we've got kind of laid out here for you is how you determine that. And so what this is going to do is kind of normalize the variability of data sets when you're calculating a standard deviation. Are you going to have to do this when you walk into your job the very first day? No. This is something that's going to be done more the quality management group. Whoever is in charge of your quality management is going to be the one that's kind of assessing some of this stuff. Now, is this something that you need to know for your certification exam? Yes. You've got to understand what goes into this whole QC quality assessment process. And so understanding the dynamics of what goes into assessing a particular analyte or methodology for your laboratory means that you kind of got to understand what this terminology is and what is being looked for when determining whether or not a test should be put out there for public use. Part of that process is determining what your control ranges are. So this is going to be where you actually assess that particular material and you're looking for looking to see, is this sufficient to determine my particular value that I'm looking for. So it could be a reference range, it could be a reference range for your patient, your QC material, but you're looking to assess to make sure everything falls within that normal bell-shaped curve, that normal 95% interval that you're looking at. So this is going to kind of help you set the standards for your QC material policy in your laboratory, because it kind of starts to give you a range that you want to fall in. So this statistical analysis is going to be done within your laboratory using some of these formulas and things. Yes, there are systems out there, computer systems, that will do this for you, but you've got to understand the method behind it. You've got to understand the math behind it, because this could be part of your role, looking at this. So you got to understand when you're evaluating QC data, what went into determining those values. And so it also helps you determine some of the sources of error that could be happening to cause these values to get skewed, which could be things like sampling errors, or any sort of procedural error that happens. So you've kind of got to know all the ins and outs of all this, and these are good questions that will pop up on your registry exam. So once you've done all your statistical data and you've determined what your ranges are and you've set up your quality assessment program within your lab, well, then you're responsible for monitoring it. So what you'll do is you'll kind of monitor it on a daily basis. Now, depending on what your policy is for your facility, it could go beyond outside of monitoring it daily because you've got other things that are in place, clear regulations in which there's some sort of management position of someone that has to evaluate it behind those who are actually running it. But by understanding what goes into it kind of helps you to evaluate this data to catch errors early. So most laboratories are going to run QC daily, and it's going to be plotted. Usually the machine plots it now, but you do need to kind of understand how to do it manually. You could work at a physician's office where maybe the machine doesn't plot it for you, so you might have to plot it yourself. So you got to understand how to plot it, what goes into figuring out those values, and what to do if it's outside of those values. So what we use is a Levy-Jennings chart, and it's something similar to what you see here. And what that does is it kind of gives you a visual for plotting that data. And then it helps you to kind of visualize when something is out. So you see here where we discuss that mean, determining that mean, which is your average. And then beyond that, you have your standard deviations. So you have your plus side and your minus side. So when we talk about these standard deviations, we're going to get a little bit more detail of what these actually mean as we go forward. But you see here at the bottom, you got days of the month. So, you know, it could be that you're plotting each day, or it could be a shift. You could be plotting something first, second, third shift. But for the most part, these will all look pretty similar. So if a lab decides to bring on a new test, when they bring on that test, there's a lot of processes that go into evaluating that test before you actually start running patients. And so part of that is the statistical data. Another part of that is making sure that you've done various validation processes, and that's from beginning to end. You're validating to make sure that everything in that process runs smoothly, that you are reproducing the same results over and over again, so you're checking those confidence interval limits, and that procedure that you put in place establishes what's acceptable. So you're looking at things like different specimens that you use. If you use this specimen, is it going to cause these results to be skewed in any way? Are you following the manufacturer's recommendations? Have you set reference limits for your patient results, or your reference range for your patient results for the particular population you have in your area? So this can vary from one area to the next. You know, you do find that different ethnicities may run in a certain range versus another ethnicity. So these are all things that are looked at when you're setting up a new test method. And then you have to validate that test method within the computer system. So there's a lot of validation processes that happen before you actually start running a test. And this could take weeks to months to get these new test methods in place. And it's usually months and months of planning before you ever actually get the analyzer into the lab and start running that new analyte. Now, you will monitor quality control on a regular basis, and when you're monitoring it, you're looking for things like shifts, trends, dispersions, anything that kind of starts making your quality control start to skew a little bit. So by using these Levy-Jennings charts, it kind of gives you a visual. Now, while you can look at a numerical value and probably assess it pretty well, when you kind of have this chart visual, it kind of helps you to kind of see a visual pattern of anything that could be causing your results to go askew. So when we talk about something like a shift, it's a sudden change. And so it's usually one direction or the other. So with a shift, let's just say we are looking at this top chart here. So you've kind of got this little area here where you've got stuff that are just shifting all over the place. So we run it one day, we're pretty close to the mean. The next day it goes up. The next day it goes down close to the mean again. Then it goes up, and then it goes down, and then it goes up. So you see some kind of shift that's happening. Versus a trend, when we look at this data down here at the bottom, you can see this little trend here where all of a sudden each day you run it, it's going down more and more and more. So once you start seeing some of these things, it may kind of flag you that maybe you need to look at something. When we talk about a systemic drift or trend, then it's basically they're progressively moving in the same direction. So this second chart here demonstrates more of a trend downward. So this kind of flags us that we need to look at something. So some of the things that we might need to look at will be the validity of that control sample. So one of our things that we might do would be to make up a new control material to see if maybe the integrity or validity of that particular material in that control matrix is kind of starting to deteriorate. Maybe it's getting close to its expiration date, so there could be a variety of factors. Or maybe you've got a lamp in your machine that's starting to go bad, and so maybe you need to change that lamp. So when we talk about this top figure here, you can see where it's sporadically kind of all over the place, and then it kind of levels out. Well, maybe they changed something. Maybe they saw that something was going on, so something was changed somewhere in this point to kind of level that out. So maybe they made up new controls, or it could be a difference. Something like this could be the time of day that it was tested. So maybe you're finding that during the early morning hours when all your machines are running at the same time because you're getting all those early morning samples in, and the room is heating up, so it's causing some variations in room temperature, which maybe are affecting your temperature of your machine. So that might be something that you need to look at. Maybe the air conditioner was down for a few days, and that could have caused some of your errors there. But whatever it is, it's something to visually flag you that, hey, I need to pay attention that something is going on, and my results for my patient may not be accurate. So if you run quality control and it violates any of the rules that are set forth for your laboratory or QC rules in general, then that kind of flags you that, hey, my quality control material is not giving me the results that I expect. So therefore, if I run my patient, those results probably aren't accurate. So maybe I need to look at a few things, not run those patients until I make sure that my analyzer is performing as required or as expected. And so part of that quality control procedure process is to actually evaluate and look at those results. So you'll run QC, get a report, look at it, and it's going to tell you if it's within acceptable limits. If it's not in acceptable limits, then you need to start looking at some things. So this may be doing some look backs, looking to see what made that error happen. Did you change the kit that you were using or those reagents? You've got a new lot number. Did you just make up new control materials? Maybe you pipetted too much deionized water into your control material. Maybe there's something on the machine that's messing up. Maybe, like I mentioned earlier, something in the temperature of the room or humidity or something is changing at a certain point in the day, so you need to look at environmental factors. So you would go through a process of trying to evaluate and troubleshoot. So you may follow the manufacturer guidelines, or it could be that your lab has a particular flow chart that they want you to follow, which may include the first step to make up new controls, look at this, and this. Maybe you need to put new reagents on the machine. Maybe it's time for maintenance. Maybe you're 2 or 3 days away from a required maintenance schedule of something that needs to be changed on the machine. Maybe the light bulb is due to be changed in 2 or 3 days, so maybe you want to do that a little early. So there's some things that you should do to kind of look at, what's my next step? What do I need to do? What do I need to look at? So it's a troubleshooting process once you start seeing that your QC values are giving you an indication that something's wrong. So what we use to kind of evaluate QC is a set of Westgard rules that were developed to kind of help you assess what could be going on. So it helps you determine if your error that's happening is random or is it systemic. So what we look at when we look at these rules is to decide, do we accept these results and go ahead and run our patients and send out those patients, or do we reject it? Do we need to do some troubleshooting because a particular rule has been violated? So we'll look at these rules and try to kind of understand them a little bit, because you will use these rules in your laboratory. You're going to run QC every shift, every department, wherever you work at. There's going to be some sort of quality control policy in place. So you need to be familiar with these rules to be able to determine if a rule has been violated and what do you need to do to kind of remedy that problem. And part of that evaluation with these Westgard rules is to understand that you're using multiple controls to kind of assess your data. So not only are we looking at it from an aspect of running, let's just say, a low and a high control, we're looking at those individually. We're looking at our control for the low. Are there shifts and trends within that low? Then we're also looking at the high individually. Are there shifts and trends within that QC material? And then we're also looking at the run itself. The run of running both of those QC data points the same day, the same time. So running your low and your high at the same time, we're kind of looking at them together. Did both of them shift the same day, the same time? Then, you know, that could point more towards the machine or the environment versus the QC material itself or the reagent. So you kind of got to be able to compare the QC in general by itself. So your high level, your normal, and your low, you got to assess them individually as well as within a run, a group, those three compared together. So the multi-rule procedure is designed to improve the QC evaluation. And so we start looking at things at the 1 standard deviation, 2 standard deviation, and 3 standard deviation limits. If something hits a 3 standard deviation, it's not good. Something that reaches that far out beyond that mean means there's some serious issues starting to happen, so we need to look at it. So what we do is we kind of look at these Westgard rules that kind of help you determine, sort of like a flow chart, did it meet this rule? Did it violate this rule? So if it violates this rule, we need to move on to the next rule. And this will kind of help us determine whether or not we accept those results. So some other things that are used when evaluating QC is to look at moving averages, which uses patients' results to kind of judge the performance of the laboratory test process. And it helps to kind of identify any kind of changes in the stability of that particular test method. So this is one of the things that somebody more in that quality management role is going to look at. There's also risk-based QC, which is also going to look at patient risk based on different things that are monitored throughout that laboratory testing process. Also using that Six Sigma process to determine any sort of cutoff limits or tolerance limits within your laboratory, as far as if it's beyond, above or below this limit, then we may need to do this, this, and this. And then also establishing some sort of individualized quality control plan. So this is one of the newer CLIA requirements that has come out, in which you have to develop that quality control plan for your laboratory, which allows you to do a little bit of alterations to it beyond what the standards are, but you still have to meet at least that minimum standard of quality control testing. But it does allow you to customize it a little bit, as long as you've included the various risk assessments, you've included a quality control plan and some sort of quality assessment plan where you're constantly monitoring and looking at things to make sure that you're not getting any sort of errors that could compromise those patient results. And so that quality assessment plan not only is going to look at the analytical factors, but also your non-analytical factors that could cause any sort of error in that testing process. And so this is going to include things like making sure you have qualified personnel. So CLIA does state what the education requirements are for particular test methodology. So if something is a moderate or high complexity, it has different educational and training requirements behind it versus a moderate or waived type testing. Making sure that you have policies and procedures in place, that there is a policy laboratory procedure manual that everyone can access, that you're evaluating the test requisitions, the ordering process, making sure they're complete, all your information is there, making sure patients are properly identified, making sure the specimens are properly prepared, any kind of prep work that goes into any sort of procedure, storage requirements, specimen transport, any sort of maintenance on equipment, making sure that your methodologies are assessed properly. So there's a whole big picture that goes into quality assessment that you have to look at that's beyond the actual test itself. And ultimately, everything's going to lead to your testing outcomes. And so this is where you're going to establish things like reference ranges or your reference values. And so this can vary from one laboratory to the next. It can depend on your geographical location. But each laboratory has to assess all of these various factors, and then they have to be able to provide this information to the physician when they're assessing the reference ranges for the patient. They have to provide this information to the physician. So if a result is sent out, it's also going to include reference ranges or those reference values for that particular laboratory, because that laboratory has done all the assessment for that area and that patient population in that area. So when you develop those reference values, these are kind of known as your normal values for your patient, and this is all done using those statistical tools, those statistical calculations, and when you're just getting a sampling of what's considered a normal group or population within that area, and then you're kind of comparing all of that data. So that does go into this quality assessment process.